Before we begin our fabulous lesson on function rules, begin with this warm-up. You're going to be graphing data from a data table. You're going to be completing a table based upon a pattern. And then I would like you to think about function machines. I've introduced them before, but think of some real-life machines that operate or do something and fill in that table. Pause the video and come back when you're done. Here's the answers, perhaps, for number 1 that you should have come up with. Graphed there. And then the table threw you for a loop with number 50. This table might require you to write an equation for what's going on there. And then finally, looking at machines in our real life that operate on things to make them better. My examples were, if you input water into a freezer, out comes ice. You put wet clothes in a dryer, out comes dry clothes. Or cold soup in a microwave will give you an output of hot soup. This lesson is on writing function rules, and that's a fancy name for an equation based upon some pattern that you're looking at. Here you have a pattern of dots, and here it says that n equals 1, and then we add dots to it and n equals 2. Adding more dots to it, you get n equals 3. Could you predict what this picture looks like for n equals 4 or n equals 5? Take a minute, pause the video, and actually draw out what n equals 4 would look like, and then what n equals 5 would look like, maybe down here. Pause the video. Well, this was me trying to make nice circles. There were other ways possibly to think about this problem, but what I began by seeing in the pattern was that the base had 3 in them. And each time vertically we would add a row. So here was 1 row, here was 2 rows, here's 3 rows, and here's 4 rows. And then we had to add 1 more at the top. That was the pattern that I saw. Perhaps you saw it in a different way, which is totally fine. Well, from this, we need to decide how we could write what's called a function rule. Again, a fancy name for an equation based on it. So you could either try to just write one down, or you might want to make a table of what's going on. So if I put 1 in, or n equaled 1, I had 4 dots coming out. When I said n equaled 2, you had 7 coming out. When I said, or had, n equals 3, I had 10 dots, and for 4 I had 13 dots, and 5 I had 16 dots. So we'd want to write a function rule to predict what n equals 50 was. We would certainly not want to draw all those patterns out. So there's a couple ways to do this. You could look at the table and see that each time you're adding 3 to those numbers in the output section. So that's telling us something there, that you're changing by 3 each time. And then if you looked at the pattern, you can see that you had 1 left over at the top there. So we'd have to account for that as well. Well, the function rule for this is that your output was 3 times your input plus 1 more. So stare at that function rule a little bit. Sometimes you have to guess and check to get them. You can use logic to get them. But now we could easily figure out what n equals 50 would be. We could predict using our function rule or equation for n equals 50. And so we'd take 50 times 3 plus that 1 little extra dot we're going to get at the top. So you would end up with 151. Here's another example like the last one, and perhaps if you're sitting next to someone, you could dig into it with them and see what their thoughts are. But your job is to draw the next 2 figures on the grid and complete the table and the function rule that would match the pattern. Pause the video now and don't give up. I know this stuff can be hard, but persevere. Did you come up with an answer that looked anything like that? I think I accidentally have an extra dot here. Ignore this one, please. Alright, so I drew out my patterns at the bottom. What I did notice off the bat was that this side had one more than the n value. So for n equals 4, I knew I needed 5 dots here, and for n equals 5, I knew I needed 6 dots there. And then from the input-output table, I started to see there was a pattern of 2 there, which made me think, well, these were double, these wings, but this one dot in the middle was the extra 1 that added to the number of dots. Now using this function rule, we can easily predict what n equals 20 would look like by substituting 20 in for n, and you would end up with 41. And it's so important to be able to come up with function rules so that you're not just continuously drawing these patterns out. Mathematics is supposed to make your life easier. Alright, here's one final example by looking at patterns from pictures. So go ahead and pause the video and try to do this one again by using the same techniques from before. Pause the video. Hopefully you drew out the n equals 5. The thing I noticed with this pattern is you had your 1 in the center, and the number value for n is how many dots you had to the right, above that middle dot, to the left, and then down below. So then I noticed maybe to come up with the pattern, all I had to do was multiply 4 times the number of dots around that center circle, or center dot. And so 4 times 5 would give me 20, plus that 1 more would give me 21. So knowing that I was always multiplying my n value by the 4 branches around the center dot helped me to write this part, and then adding 1, which was always my center circle. So I can predict now using this equation for 20. So you would end up with 81. Let's look at these things, writing function rules with tables. In the first example here, and I think we'll just do that one, it asks us to model this function rule, y equals 1/2 x plus 3, using a table of values and a graph. So now we're working backwards, where we're given the rule and we're going to make a table from it, and then a graph will come out. When they do not give you domain values for x, you just pick whatever you want. So I'll pick a -2, I'll pick a 0, I'll pick a 1, and we'll pick one more, maybe like a 2. So you take those domain values and you substitute them in your function rule. So if I have y equals 1/2 a -2 plus 3, you will end up with a -1 plus 3, and your output will be a 2. Substituting a 0 in, this whole thing will go away, leaving you with 3. If I substitute a 1 in for x, I'm going to get 1/2 plus 3, which is 3.5. And if I substitute a 2 in for x, well, 1/2 of 2 is 1, plus 3 is 4. And then you can show what that pattern looks like when you graph it by just making the coordinate pairs. And mine never looks good on this machine, but you'll understand. And then 2 and a 4. So your function rule is modeled in a graph that looks like that. You can also model function rules with word problems. It says suppose your group recorded a CD and now you want to sell it. One company charges $250 for making a master CD and designing the art for the cover. There is also a $3 cost to burn each CD. I think that's a typo. The total cost, P of C, depends on the number of discs or CDs C burned. Now it seems like a scary problem when you read it and you want to shut down, I understand, but most of the time in these problems they're going to give you your function rule right there. So P of C, that means what is the cost, or what is your total cost, P, depending on your number of CDs that you make. So you know that was $250 no matter what for mastering the CD and designing the art, and then it cost you another $3 to burn each CD. If you're asked to make a table of values, well, we're not going to use x's, are we? We're going to use a C and a P of C. Remember, P of C is just Y. C is the number of CDs burned. It would make no sense to pick a domain that was negative. I cannot burn negative CDs. I certainly could burn none of them, or 1, 2, or 3 of them. So your domain values really need to make sense when you're modeling based upon a real-life situation. So if I evaluate P of C, that means wherever I see a C, for this first one, I'm going to put a 0 in there, and that 3 times 0 goes away, and you're just paying that initial cost of $250. If I make one CD, it'll be $253. If I make 2 CDs, it's going to be $256 and $259. Now that's kind of hard to graph on the coordinate plane I gave you. So it's actually really bad. I wish I could draw over it, but let's ignore that those coordinate grids are there, and I'm going to change it to looking only at quadrant 1. There's no reason to have quadrant 2 or 3, because I'll never have any negative x values. So do your best to ignore that coordinate grid. And I'll start with 0. I'm going to skip every other one, so we can actually see. And then because I'm going up, I start at 250. I'm going to break my scale, which we've talked about. And I'll start at 250, 251. I think I'm skipping every other one again. And I'm going to have to go above it. But we certainly can graph these. It won't be pretty, but we'll do it. And I'll choose green so you can see it. So if I'm at 0 and 250, I have a coordinate pair right there. And 1 and 253 would be there. 2 and 256. And 3 and 259. It's going to be way up there. So all those previous examples are ways that you could see problems involving function rules, and remember that just means it's a fancy word for an equation. Sometimes you might be given a table and be asked to write a function rule for what's going on in the table. Well, there's a couple tricks sometimes to see it. You're looking for patterns or differences between your x values and patterns or differences between your y values. So what do we notice? Our x values are going up by 1, and our y values are also going up by 1. Most function rules begin with y equals. And I'm multiplying something or subtracting something from my x value to get this y value. And you have to kind of use logic here. If I had an x value like 1, how did I end up with a negative 1? If I had an x value of 2, how did I end up with 0? Well, maybe you see the difference between these is 2. So whatever x value you have, if you take away 2, you should end up with your y value. Well, that turns out to be the case, and you should always check yourself to make sure you're actually right. Do a quick little mental check. So if I put in 1 and take away 2, I end up with negative 1. If I put in a 3 for x and take away 2, I do end up with 1, and so on. So this actually does work, and we can say that that's our function rule for that table. You can go ahead and try this one yourself, otherwise I'll do it with you, but maybe you want to ignore me while I do it. Those are still going up by 1. These are going up by 2, so there's a definite pattern here. So I have some input, and I end up with 2 for the output. I input 2 and my output is 4. I input a 3 and my output is 6, so maybe you can see here that I'm actually doubling my value of x. Well, that's what that equation or function rule would look like. So again, it's a little bit of logic and a little bit of luck. And sometimes you have to guess and check, and they definitely get more complicated. But don't let that stop you. There's a rule there, and you can figure it out.